Welcome back to the deep dive. So today we're tackling something a little different, not speed, but distance.
Right. A lot of distance.
Yeah, exactly. I mean, how do you send a sensitive radio signal, let's say 40 kilometers away, and have it arrive in one piece?
And not just in one piece, but in better shape than if you'd sent it across the street on the wrong cable.
Okay, so our source for this is the technical blueprint for the Thor Broadcast F-RFOF-6GHZ-TXRX. That's a mouthful.
It is, but our mission is to get what RF over fiber or RFOF actually is. It's, a pretty radical solution to a fundamental physics problem.
And that problem is signal degradation, right? That an electrical signal just falls apart over long distances.
It becomes unusable static. That's the challenge.
So why can't we just, I don't know, use a massive amplifier on a standard copper cable?
You could, but you just end up amplifying all the noise along with the signal. Every kilometer adds more loss, more distortion. It's a losing battle.
Oh, okay.
The magic of RFOF is that it changes the medium entirely.
So we're not using copper for the long stretch.
Exactly. The transmitter takes your radio frequency signal and it converts it into an optical signal. Basically, it turns your radio wave into a focus beam of light.
So we stop worrying about electron flow and start using photon flow.
Precisely. That light travels over a single-mode fiber optic cable, which has, astronomically low signal loss compared to copper.
And this unit specifies transmission up to 40 kilometers.
40 kilometers. And on the far end, the receiver converts that light signal perfectly back into a clean RF signal. We're using a specific wavelength here, 1310 nanometers, to do it super efficiently.
That flexibility just seems incredible. You're bypassing 40 kilometers of electrical resistance.
And the source material notes how, easy and cost-effective this is. You can use fiber splitters for these complex setups.
So it's not just a simple point-to-point connection.
No, you can do multi-point distribution across a huge area.
Okay, so this brings us to the application. If you have that much flexibility, what kinds of signals are important enough to need this?
Well, that's where the other key spec comes in, the frequency range.
Right, it's huge. The spec sheet says 100 megahertz all the way up to 6 gigahertz.
And that wide range is exactly why it's so critical for these massive global systems. We're talking L-band and S-band satellite communications.
So things like GPS and mobile connectivity.
Yep. And also for things like radio telescopes, collecting these incredibly faint signals from deep space, or just distributing RF antenna signals across a huge government campus.
And the physical design has to support that, I assume.
It does. It's listed as ultra-compact, very low power consumption. The transmitter uses under half a watt.
But two technical details in the source really stood out to me. It's flat frequency response and excellent EMC design.
Okay, those are crucial. The EMC part just means it's electrically quiet. It won't interfere with other sensitive gear nearby.
It plays nice with others.
Exactly, and that flat frequency response means it preserves the signal's integrity. What you put in is what you get out, just 40 kilometers later.
So let's connect this to the bigger picture then.
Yeah.
So what here is that this tech transforms radio waves,
which are limited by distance and copper,
into light. And that creates a functionally lossless communication backbone for these really sensitive long-distance applications.
It's the difference between a high-stakes signal becoming background noise versus being heard perfectly clear. And that's all about maintaining a low-noise figure, which this equipment does.
So a low-noise figure means the gear itself isn't adding static and drowning out the faint signal you're trying to catch.
You got it. The signal's fidelity is maintained over that whole journey.
So here's a final thought for you to mull over. We know this tech is absolutely essential for things like accurate GPS and precise timing synchronization.
Across massive distances, yeah.
Then consider how much of our modern world, our global infrastructure, really relies on this silent, persistent conversion of radio waves into light. Everything from coordinating global shipping to making sure high-frequency trading platforms stay perfectly synchronized, down to the microsecond. It's all running on a literal light speed requirement for the modern world.